For the models of crystalline solids activity, be sure to get out your Chapter 10 lecture handout and reread the section on metallic solids. There is a very handy table on page 18 that you will find indispensable in working with crystalline solids. Alrighty, so we are primarily working with 3D solids, but we start just to give you an introduction with two-dimensional lattices. A basic understanding of some of the concepts in this activity can be obtained from a simple two-dimensional lattice, such as circular objects, such as pennies as the model. There are two ways of packing circular objects as shown in Figure 1. So either the one on the right or the one on the left. The one on the right has more empty space than the one on the, the one on the right on the left has more empty space than the one on the right, because you see the one on the right, the second row of pennies is put into the dimples of the first row. The third row is in the dimples of the second row, etc. So the unit cell is the simplest repeating unit that contains all the information to reproduce the lattice if extended in the x and y directions. So we see that for the first lattice, the one on the right, number 1 there, a good unit cell is to use that cube, that box that's shown. A good unit cell to use for the array number 2 is the rectangular box that contains 4 corners plus the middle penny. Okay, coordination number. That is the number of circles that a circle touches. So go to the dark circle in the middle of Figure 3. This is array 1, the less tightly packed one. So the dark circle there in the middle, you see that it is touching 4 other circles. So for this array, we would say the coordination number is 4. Packing efficiency of a given arrangement can be quantitatively determined using equation 1 below. The packing efficiency is the percentage of occupied space in a unit cell. So the packing efficiency for the two-dimensional arrays is the total area of the circles in the unit cell divided by the total area of the unit cell times 100. Okay, sample problem. Calculate the packing efficiency for the following arrangement. That would be called like lattice 1, using the unit cell shown. Okay, so the area of the circles is going to be the number of equivalent circles in the unit cell times the equation of a circle, which is pi r squared. So we see that our unit cell has 4 corners, and each corner is 1/4 of a circle. So that gives the equivalence of 1 circle per unit cell. And then that 1 circle times pi r squared gives, well, pi r squared as the area of the circles in that unit cell. Okay, so that's step 1. That's what will go in the numerator of our packing efficiency equation. Step 2, determine the area occupied by the unit cell itself in terms of the circle radius r. So the area is the length times the width. Well, it's a square, so we have equal length, so we have length squared. In terms of r, we see length equals 2r. So then we have the area of the unit cell is the quantity 2r squared or 4r squared. Alrighty, so now we put all that together in our packing efficiency equation, step 3. So the area of the circles divided by the area of the unit cell times 100. So the area of the circles we found to be pi r squared. The area of the unit cell, 4r squared. Notice the r squared cancels out, and we do that times 100. So basically we have pi times 100 over 4, or we have 78.8% of the available space occupied. So note that it's not important to know the exact size of the circles, as the circle radius cancels out. So it doesn't matter how big the circles are. If they are packed that way, then they're going to have 78.5% of the available space occupied. In the previous sample problem, the length of the unit cell could be easily determined in terms of the radius r because there is no empty space between the circles. Let's go back to that unit cell. We could look at the unit cell and just see what a length is in terms of r. Sometimes, depending on the lattice, there's empty space between the circles, and so it turns out that we have to end up using the Pythagorean theorem. And that an example like this is in the chapter 10 handout. Okay, so now we move into three-dimensional lattices. The packing of spheres, like atoms instead of circles, is more complex to visualize, but use the same principles as with two-dimensional packing. 3D unit cells are typically based on regular polyhedrons, such as cubes, hexagonal prisms, and so forth. There are 14 common unit cells in what's called the Bravais system. And in this activity, our discussion is limited to the following: simple cubic, so it's a cube; face-centered cubic, also a cube; body-centered cubic, also a cube; and hexagonal closest packing. That's not a cube. So simple cubic, we abbreviate SC; face-centered cubic, FCC; body-centered cubic, BCC; hexagonal closest packing, HCP. We will only make calculations with the cubic ones. Okay, so the analysis of the 3D models has a few differences compared to analyzing 2D models. When calculating the space taken up by the spheres, volume should be used instead of area. So that would be shown in equation 2 here. The volume of the spheres is the number of spheres in that unit cell times the volume of a sphere in terms of r, 4/3 pi r cubed. You probably learned that in a math class. The space taken up by certain sphere segments is summarized in table 1. Volume instead of area should also be used when calculating the packing efficiency, equation 3. So packing efficiency, it has to do with the amount occupied versus what is the amount times 100. So we have the volume of the spheres, which is the number of spheres in the unit cell times 4/3 pi r cubed, divided by the volume of the unit cells in terms of r, the radius, times 100. Okay, so table 1 is showing looking at what portion of a sphere has the arrow to it. In the first diagram, we have the corner being referred to. 1/8 of a corner in 3 dimensions is part of that unit cell. The other 7/8 are parts of other adjacent unit cells. So just like in our chapter 10 handout, keep in mind that corner pieces are 1/8 of the sphere in that unit cell. If we have a face that we're referring to, that comes up in the face-centered cubic, 1/2 of that is in the unit cell. This last one is showing that an edge piece, that comes up when we have the ionic solids. And when we have what's referred to here as an edge piece, 1/4 of of a sphere, of that sphere, is in that unit cell. So come back and look at this table 1 as needed. Okay, so ionic solids, when packing spheres of the same size, there's often a considerable amount of unused empty space. Many ionic solids combine ions of different sizes and utilize the empty space more efficiently. Anions are typically larger than the cations because they take on an electron, whereas the cation loses. So the anion's typically bigger than the cation. So the anions define the unit cell. The cations occupy holes in the structure such that they maximize the cation-anion attractions and minimize the anion-anion repulsions. Alrighty. The unit cell of an ionic crystal can be used to determine the ion's chemical formula through adding the total number of cations and anions present. So what we do is we figure out within a unit cell of an ionic solid how many total equivalent anions are there, how many total equivalent cations are there. If there's the same number of cations as anions, then we know the ratio between them is 1:1, like in NaCl, for example. Okay, application to density. The density of a crystalline solid can be calculated by determining the mass of the atoms in the unit cell and dividing it by the volume of the unit cell. So density, mass over volume. So we have the mass of the atoms in the unit cell divided by the volume of the unit cell. We would want the mass to be in units of grams, the volume to be in units of centimeters cubed, and we get our grams per centimeter cubed density that we're used to. To determine the mass of the atoms, you must note that each type of cubic unit cell can accommodate different numbers of atoms. So we will see, as is described in the chapter 10 lecture handout, that when we have simple cubic, we have the equivalent of 1 atom per cell. When we have face-centered cubic, we have the equivalent of 4 atoms per cell. And when we have body-centered cubic, we have the equivalent of 2 atoms per cell. So this hypothetical example with 8 atoms, 6 atoms, none of the 3 have 6 atoms per unit cell, but this is just showing you the dimensional analysis step that we would do to figure out the mass. So if there were 6 atoms, well, we would then convert those atoms to moles with Avogadro's number, so we divide by Avogadro's number. Now we're at moles, then we would use the molar mass of that solid. Here it's shown as 16.00 grams per mole. And you notice that units work out where we have just grams left over. It's grams per unit cell. So that's what would go in the numerator of equation 4 for the density. And in this class, we are limiting the application to cubic unit cells, so simple cubic, face-centered cubic, body-centered cubic. Thus, the volume of the unit cell is always the volume of a cube. So we have equation 6 applies. We just figure out what the length is in terms of r, which is in your chapter 10 lecture handout notes. So volume is L cubed. Note that this requires you to know the length of the unit cell in terms of r. Okay, so that's in the table on page 18 in your chapter 10 lecture handout notes. Real crystals. There is a question that alludes to real crystals, so refer to this paragraph here. Real crystals have lattice defects, which can include a point in a lattice that is not occupied. That's a vacancy defect. They can include areas where the lattice is deformed, a dislocation defect, or even atoms, including impurities, which occupy sites that are not usually occupied. Those are called interstitial defects. All of these can affect the density of a metal, that is the experimental density. Okay, so a little bit more information that we will need. Activity diagrams, part A, metallic crystals. Okay, so use a provided model. Well, we don't have the model. We just have these diagrams shown in this lab write-up, and you have a lot of diagrams shown in the Chapter 10 lecture handout, especially that table I've been referring to. This lattice is, oh, for simple cubic. Okay, so that's the SC1, the simple cubic. It turns out that this lattice is not common in nature, but it is the structure for the metal polonium. So what we have for it are a layer where the balls are touching each other, and then we put another layer directly on top, so not in the dimples, directly on top. So the unit cell is what's shown with green there. We see there are 8 corner atoms, and 1/8 of a corner atom is in the cell, so we have 8 times an eighth, or we have the equivalent of 1 unit cell, 1 atom per unit cell. Also, we see that the length of a unit cell in terms of R is 2R. So for simple cubic, the length is 2R. Face-centered cubic, so we see that shown as the layers purple, yellow, red, and then we have purple, yellow, red repeating over and over. If we flip that on its side, we end up getting the face-centered cubic unit cell, which is shown in the green and blue. Of course, all those atoms that those balls represent are the same, so picture them to be all the same color. They're just shown as different colors so you can distinguish the face balls from the corner balls. Now, looking at how many atoms per cell we have, well, we have 8 corner atoms times an eighth, and then we have 6 face atoms times a half, so that means we have 1 plus 3, or we have 4 atoms per FCC unit cell. And our length in terms of R, as we went through in the Chapter 10 lecture handout, is length equals 2.828 R. For body-centered cubic, so we have no face atoms, but we have a ball atom. So we have 8 corner atoms times an eighth plus the 1 ball that's in the center. So we have the equivalent of 2 atoms per BCC unit cell. And as your notes, the Chapter 10 lecture handout notes show you, the length in terms of R for body-centered is L equals 2.309 R. In hexagonal closest packing, it's very similar to face-centered cubic, FCC, in that the packing efficiency is the same. You will calculate the packing efficiency for FCC. You won't calculate it for HCP. Rather, you will just know that the values are the same because the layers and the dimples, a lot of it is the same. But in the end, we have some differences, so we end up with not a cube. For the unit cell, calculations would be a lot harder, so we're not making any calculations with HCP. We just know that its packing efficiency is the same as with FCC. It turns out the coordination number of HCP and FCC are also the same. Okay, part B, we're working with ionic crystals. The sodium chloride crystal structure is typical of ionic solids and can be visualized by stacking layers 1, 2, and 3, shown in figure 9, in order so that the large spheres form the face-centered cubic arrangement. So the large spheres are the chloride ions, and that's FCC. And the holes in between are where the sodium ions go. Now notice that we have the sodium ions represented by the yellow balls, or the smaller balls shown in the layers 1, 2, and 3 on the left. The smaller balls, well, there's one in the middle layer. In layer 2, there's a yellow ball in the middle that we can't see in the green and yellow diagram. We will have to remember that it's there for a question that's asked of us later on. Okay, so the pre-activity, as usual, skip, unless you want to look it over. So here's the report. So we are working first with the simple cubic, and based on that diagram we see here, or based on others that you see in the introduction, or based on your Chapter 10 lecture handouts, figure out what the coordination number is and the number of atoms in the cell. Well, they were described to you above. The volume of the atoms in terms of the spherical radius, in terms of the sphere radius r. So that is going to be the number of atoms in the simple cubic times 4/3 pi r cubed. Show your calculation, show the answer on the right. The length of the unit cell in terms of r. And then we have the volume of the cubic unit cell in terms of the radius. So volume is length cubed, so whatever you have for the length above, cube that. Then you're calculating the packing efficiency. So that is the volume of the atoms divided by the volume of the unit cell times 100. Okay, and then we're doing the same thing for the face-centered cubic, figuring out the number of atoms in the unit cell, the coordination number, the volume of the atoms. So the number of atoms times 4/3 pi r cubed, that's what goes in the volume of the atoms. The length of the cell, L in terms of r, we described that above. Then the volume of the unit cell, which is whatever you have for the length in the above one in terms of r, cube that. Packing efficiency, so that would be the volume of the atoms divided by the volume of the unit cell times 100. Do the same thing for body-centered cubic. Then we have the ionic crystal, part B. So you're in the A, you are asked to calculate the number of chloride ions present. Okay, so those are the green ones, the number of equivalent chloride ions. It's FCC. So we have the 8 corner times an eighth, plus we have the 6 faces times a half. B, calculate the number of sodium atoms present. Those are the yellow balls. So we have 12 edge atoms. Each edge is 1/4 in the unit cell, plus we have that yellow ball in the very center. Based on your answers above, what is the empirical formula for sodium chloride? So what's the ratio of sodium to chloride? Okay, so number 1, now you're asked to think about the HCP unit cell and figure out what the coordination number is and the packing efficiency. You are not calculating the packing efficiency. You are remembering what we talked about before in its comparison to FCC. Number 2, the density of diamond is 3.52 grams per cubic centimeter, and the volume of a unit cell is 4.54 times 10 to the 7th picometers cubed. Now, a pico is 10 to the minus 12. So convert that to centimeters cubed, and you'll be able to ultimately figure out the number of carbon atoms present in the unit cell. It's a dimensional analysis problem for the most part. Number 3, crystals of copper metal have the FCC unit cell. So you're calculating the density of copper in grams per cubic centimeter given the radius of the copper atom is 128 picometers. Again, a pico is 10 to the minus 12. And that problem is described very well, I think, in the Chapter 10 lecture handout. There's a problem or two where we're calculating densities. So look over those notes. Also look in the introduction above. It talks about density. So you will calculate that theoretical density, and then we have that the actual literature value is 8.96 grams per cubic centimeter. How does your calculated result compare to this? I think you'll find it very similar. Number 4 is give some differences between, or some reasons that the real density from B above would be different from your theoretical one. So go back to the real crystals part that we referred to above. Alrighty, so check out your answers, make sure you're happy with them, and when you're done, scan this as a PDF file and submit it.